welcome in. Some nights seem built for dim rooms and unusual histories. No rush here. The small details can arrive before the larger meaning does. And before we begin, a small note of care. For the quality of your sleep, this video has been made with dim, low-light visuals, slow movement, and a soft, calm voice. Nothing here is meant to tug you awake. You can listen closely, or let the details drift by. You can leave a small note with where in the world you are listening from, if you are comfortable sharing it generally. If this helps you rest, subscribing lets the channel know to keep making more slow stories like this. Now, let's begin. Chapter 1. The first people who tried listening to the human brain did not begin with glowing scanners or sleek machines. They began with wires pulled from desk drawers, rubber-coated leads, metal discs, conductive paste cold against the scalp, long paper rolls waiting for movement. The whole thing looked improvised, almost disappointing, considering the object they were trying to study. Because the brain does not feel like a physical object when you experience it from the inside. It feels like a self, a point of view, a consciousness suspended somewhere behind the eyes. But in the early sleep labs of the 1920s, consciousness reduced itself into static. Small rooms, dim lamps, the smell of dust, paper, warm electronics, and stale coffee. Researchers leaning over strange machines late into the night, while thin ink lines scratched across moving paper. Hans Berger, one of the first people to successfully record electrical activity from a living human brain, spent years convinced that thoughts might leave measurable traces. At the time, the idea sounded almost mystical. How could memory, fear, imagination, dreams, or identity become electrical patterns on paper? And yet, slowly, the brain began exposing itself. An EEG, electroencephalogram, works through an idea that still feels strange today. Every thought, sensation, dream, fear, and decision emerges from billions of neurons exchanging electrical signals. Tiny voltage changes ripple across enormous biological networks, and some of that activity reaches the scalp where electrodes can detect it. Not thoughts directly, not memories, not meaning, just waves. The first recordings barely looked scientific at all. Uneven squiggles, chaotic lines trembling across paper rolls like weak radio interference. Most people looking at them saw noise, but hidden inside the static were patterns. When someone closed their eyes, the waves shifted. When they solved a problem, the rhythms changed. When they drifted towards sleep, slower tides emerged from the chaos. The brain, it turned out, never truly became silent. Even unconsciousness had structure. That realization changed everything. Because before EEG recordings, sleep was often imagined as a kind of shutdown state, a passive absence. But the electrical patterns revealed something far stranger. The sleeping brain remained intensely active, cycling through repeating stages, generating rhythms, reorganizing information, constructing dreams. The body rested. The brain continued building worlds. And there's something deeply eerie about those early recordings when you think about what they actually captured. A volunteer sits alone in a dim room with wires attached to their head. They begin falling asleep. Their conscious awareness dissolves. Dreams emerge. Memories reactivate. Entire realities appear internally. And outside the skull, a machine quietly records flickering voltage changes measured in microvolts. That contrast never stops being strange, because somewhere inside those faint electrical storms exists the feeling of becoming afraid in a nightmare, the memory of childhood, the sound of your own name, the sense that you are a person, the experience of being alive at all. The more neuroscience advances, the less solid consciousness begins to feel. The EEG revealed something unsettling very early. Your inner life has physical signatures. Thoughts are not floating abstractions detached from biology. Change the electrical activity, and perception changes. Damage certain regions, and personality changes. Interrupt specific networks, and consciousness itself can fracture. The self is not hovering above the brain. It emerges from it. And yet the deeper researchers looked, the stranger the problem became, because EEG machines could detect activity, but not explain experience. They could show when dreaming started, not why dreams feel real. They could measure transitions into unconsciousness, not why awareness exists in the first place. They could detect patterns linked to attention, memory, fear, sleep, and perception. But nowhere inside the waves did anyone find a clear location for the self. Only motion, signals, feedback, endless electrical conversation. And maybe that is part of what makes the brain so unsettling compared to any other object we study. A galaxy does not wonder what it is. A hurricane does not examine its own structure. A black hole does not become conscious of itself. But the human brain somehow turned inward. A 3-pound network of cells began observing its own activity and asking questions about the nature of reality itself. Even now, modern neuroscience still carries traces of those old sleep labs. The wires became digital. The machines became unimaginably more advanced. The paper rolls disappeared. But fundamentally, we are still doing the same thing, placing sensors against the surface of the skull and trying to understand how electrical activity becomes experience, trying to understand how matter becomes awareness, trying to understand how a biological system constructs an entire world internally and then mistakes that construction for direct reality. And late at night, looking at old EEG recordings, faded ink lines stretching endlessly across yellowing paper, it becomes difficult not to feel a certain kind of awe. Because every trembling wave represents billions of neurons interacting inside darkness. A hidden city of silent lightning, always active, always predicting, always generating the next version of reality. Even now, as you listen, the electrical storms inside your skull continue without pause. The brain never truly goes dark. If you would like to skip ahead a minute, now would be the time, as I'd like to talk to you about Nudge It Budget. Nudge It Budget is a free budgeting tool that runs right in your browser. No login, no linking your cards, and no collecting your personal financial data. It was built for people who want to make sense of their money without getting locked into complicated apps, subscriptions, or spreadsheets that take more work than they're worth. Nudge It Budget gives you a simple place to organize your finances, understand where your money is going, and start building toward financial independence. It is not trying to be the flashiest budgeting tool out there. It is trying to be something better, free, useful, private, and actually easy to start using. Start planning today at Nudge It Budget. Come it, and when you're done, don't forget to save your budget to your computer so you can load it back up next time. That's Nudge It Budget. Free, private, and built to help you finally get a clear picture of your finances. Chapter 2. A single neuron is almost insultingly simple. No thoughts, no personality, no dreams, no memories. Just a cell holding an electrical charge. And yet everything you have ever loved, feared, remembered, imagined, regretted, or become emerged from billions of these tiny biological switches interacting in darkness. The scale of that is difficult to emotionally process. A single neuron cannot think any more than a single water molecule can create a hurricane. But somewhere beyond a certain threshold of complexity, electrical activity stops looking like chemistry and starts looking like consciousness. That transition is one of the strangest things in the universe. Early neuroscientists discovered this gradually, often through experiments that felt oddly mechanical for something so deeply human. Electrodes. Frog legs twitching under electrical stimulation, static shocks jumping between metal surfaces, sparks moving through wet tissue. The foundations of thought looked less like philosophy and more like plumbing. A neuron works through controlled electrical instability. At rest, the cell maintains a voltage difference between its interior and the surrounding environment, using charged particles called ions, mostly sodium and potassium. Tiny molecular pumps constantly move these particles across the membrane, building tension like water accumulating behind a dam. The neuron spends energy preparing itself to fire. Then, if enough incoming signals arrive, the balance collapses. Ion channels snap open. Charge floods inward. Voltage surges down the cell in a traveling wave called an action potential. A spark. Not metaphorically. Physically, the signal races down a long extension called the axon, sometimes traveling over 100 meters per second until it reaches another neuron. And then something strange happens. The electrical signal stops. Because neurons do not actually touch each other. Between every neuron exists a microscopic gap called the synapse. An empty space so small it barely seems real. And yet every thought you have ever experienced depended on signals successfully crossing trillions of these gaps every second. Electricity becomes chemistry. The neuron releases neurotransmitters into the synapse. Molecules drift across the gap. Receptors activate. Another neuron changes its state. And from these exchanges emerge language, memory, emotion, fear, identity, music, dreams, and the feeling of being yourself. The deeper you examine the brain, the less obvious consciousness becomes. Because nowhere inside a neuron do you find a thought. You find proteins, membranes, salt gradients, chemical release mechanisms, electrical thresholds, matter interacting with matter. And yet somehow, at sufficient scale, the system begins generating an internal world. One of the strangest aspects of neurons is that they are not static components. They are constantly reshaping themselves based on experience. Every repeated thought strengthens pathways. Every memory alters structure. Every habit reinforces circuitry. The brain is not merely processing information. It is physically rewriting itself in response to existence. This is neuroplasticity. Experience becoming biology. A traumatic event can permanently alter neural pathways. So can years of practice. So can chronic fear. So can love. So can loneliness. So can addiction. Your life continuously sculpts the architecture, generating your future thoughts. And most of this happens beneath conscious awareness. That may be one of the most unsettling discoveries in neuroscience. The conscious self is not directing the majority of brain activity. The subconscious brain is constantly processing patterns, predicting outcomes, evaluating threats, generating impulses, and preparing actions before conscious awareness catches up. Experiments repeatedly show that neural activity indicating a decision can appear before a person becomes consciously aware they have made one. The action begins. Then awareness arrives, which raises an uncomfortable possibility. Consciousness may not be the author of thought. It may be the observer of processes already unfolding. And yet subjectively, it feels completely different. You experience yourself as choosing, deliberating, controlling. But underneath that experience, billions of neurons exchange signals automatically through systems shaped by genetics, memory, reinforcement, hormones, prediction, emotion, and survival. The self may emerge from the activity, not govern it. There's also something quietly beautiful about how fragile neurons are. A slight oxygen interruption can kill them. A small lesion can erase language. Damage to tiny regions can alter morality, fear, personality, or impulse control. A tumor pressing against the wrong network can transform someone into a different person entirely, which forces a disturbing realization. Identity is biological. The boundary between you and altered behavior may only be a few damaged cells wide. And yet neurons are also astonishingly resilient. The brain can reorganize itself after injury. Functions can migrate. Networks adapt. Entire sensory systems can partially rewire after damage. The system is fragile and adaptive simultaneously, a constantly changing electrical ecosystem trying to preserve continuity while rebuilding itself from within. And despite all modern neuroscience, there is still no clear explanation for why any of this should produce subjective experience at all. We understand pieces of the mechanism: electrical signaling, chemical transmission, feedback loops, network synchronization, plasticity. But explanation is not experience. You can describe every component of a hurricane without explaining what it feels like to stand inside one. Likewise, neuroscience can trace the mechanics of perception, while the deeper mystery remains untouched. Why should electrical activity feel like anything from the inside? Why should matter become awareness? Somewhere inside billions of neurons exchanging chemical and electrical signals, a model of reality emerges. Somewhere inside the sparks, the brain constructs. The sensation of color, the sound of music, the feeling of time, the memory of childhood, the fear of death, the belief that you are a singular self moving through the world. And perhaps strangest of all, the system becomes capable of observing itself. A network of cells begins asking questions about its own nature. Electricity, studying electricity. Matter attempting to understand why it became conscious in the first place. Chapter 3. The Synapse. The most important events in the human brain happen inside spaces so small they almost do not seem real. Not inside the neurons themselves. Not in the electrical sparks racing down axons, but in the gaps between cells. Tiny interruptions, microscopic pauses, spaces so narrow that thousands could fit across the width of a human hair. And somehow, inside those gaps, matter becomes thought. A synapse is the place where one neuron attempts to influence another. The electrical signal arrives at the end of the cell, but it cannot continue directly because neurons do not physically touch. Between them exists a tiny void, usually around 20 nanometers wide. The signal must somehow cross empty space. So electricity transforms into chemistry. The neuron releases neurotransmitters, molecules like dopamine, serotonin, glutamate, GABA, into the synapse. These chemicals drift across the gap and bind to receptors on the next cell, altering its electrical state. If enough signals arrive, the next neuron fires. If not, the signal dies there. Which means every thought you have ever experienced depended on trillions of microscopic negotiations succeeding at exactly the right moment. And underneath all of it, salt, ordinary ions, sodium, potassium, calcium, chloride. The same kinds of charged particles sitting inside a teaspoon of table salt on a kitchen counter. That's one of the strangest aspects of neuroscience. The mechanisms underlying consciousness are often chemically mundane. The brain does not run on glowing energy or mysterious substances. It runs on ion gradients, electrical charge differences, molecular release systems, and feedback loops refined through evolution. Your inner life depends on controlled chemical imbalance. A neuron maintains different ion concentrations inside and outside its membrane. That imbalance stores electrical potential. When channels open, ions rush across the membrane, voltage changes, and information moves. The entire system is built on separation. Separated charges, separated cells, separated compartments. Consciousness emerges from things failing to fully connect. And the brain is obsessively careful about maintaining those balances. A slight disruption in sodium levels can alter cognition. Too little oxygen and neurons begin dying within minutes. A missing neurotransmitter can collapse motivation. An excess of dopamine can distort reality itself. The difference between clarity and hallucination may only be molecular. That fragility becomes obvious in hospitals. Someone receives a saline IV. Clear fluid drips slowly into the bloodstream. Nothing dramatic appears to happen. But inside the skull, billions of neurons depend on those chemical conditions remaining stable enough to continue communicating. Shift the balance too far, and perception destabilizes. Memory fragments. Awareness becomes confused. The self is chemically vulnerable, and yet synapses are not merely passive relay points. They change constantly. Every experience slightly alters synaptic strength. Every repeated thought reinforces pathways. Every fear reaction trains future responses. Every memory modifies connectivity. The brain is not storing information like files inside drawers. It is continuously reshaping relationships between neurons. Memory is structural change. That means your experiences physically rewrite the system generating your future experiences. A traumatic event can strengthen fear circuits for decades. Repeated practice can enlarge networks associated with skill. Addiction can hijack reward pathways. Meditation can alter attention systems. Chronic stress can reshape emotional processing. Your life leaves physical traces inside synaptic architecture, and most of this occurs automatically. The subconscious brain is constantly updating predictive models based on feedback from the environment. Patterns repeat, pathways strengthen, expectations form. Eventually, the brain stops merely reacting to reality. It begins anticipating it. Modern neuroscience increasingly suggests that perception itself may be predictive rather than purely reactive. The brain generates internal models of the world and continuously updates them using incoming sensory information. In other words, you do not passively experience reality. Your brain actively constructs a version of it. That idea becomes deeply unsettling once you realize how much perception depends on filtering. The brain receives overwhelming amounts of sensory information every second, far more than conscious awareness could ever process directly. So the nervous system removes most of it automatically. You experience only a curated model, a simplified reality optimized for survival. And under certain conditions, dreams, psychedelics, psychosis, sensory deprivation, neurological disorders, those filtering systems can shift dramatically. The constructed nature of reality becomes easier to see. Dreams are perhaps the clearest example. While disconnected from the external world, the brain generates entire environments internally. People speak. Landscapes appear. Time flows. Fear feels real. Memory operates selectively. Logic partially collapses. And during the dream, you usually accept all of it as reality without hesitation, which raises an uncomfortable question. If the brain can generate convincing realities internally during sleep, how certain can you be about the stability of waking perception itself? The deeper neuroscience goes, the stranger ordinary consciousness begins to look, especially because synapses are noisy. Signals fail constantly. Neurons misfire. Messages get distorted. Networks improvise. The brain is not a perfectly engineered computer executing flawless calculations. It is more like a living ecosystem, balancing instability against coherence. And somehow, despite all the noise, continuity emerges. You wake up each morning feeling like the same person. Your memories mostly align. Your body feels like yours. The world appears stable. But underneath that experience, trillions of synapses exchange chemical signals through fragile biological systems, balanced permanently on the edge of disorder, which may explain why neurological disorders can feel so existentially disturbing. A lesion alters emotional regulation. A degenerative disease erases memory. A psychedelic compound modifies receptor activity, and suddenly reality itself changes shape. A seizure disrupts synchronized firing patterns, and consciousness temporarily disappears. The self can be chemically interrupted, and yet no neuroscientist has ever found a single location where the self definitively exists. No central observer, no hidden operator, no clear dividing line where electrical activity becomes subjective experience. Only networks influencing networks, signals crossing gaps, feedback loops reinforcing themselves across time. And somehow, from all of this, emerges the feeling of being someone. Perhaps that is why the synapse feels philosophically important in a way that goes beyond biology, because the synapse is a boundary, a place where signals pause before continuing, a place where meaning depends on successful translation, a place where information almost fails to arrive. The conscious self may exist in those gaps more than anywhere else, suspended between electrical storms, held together by chemical negotiations, a temporary pattern maintained across trillions of microscopic spaces. And even now, as you listen, countless signals continue crossing those invisible bridges inside your skull. Tiny molecular exchanges carrying memory, prediction, emotion, language, fear, imagination, and awareness itself forward through the darkness, one gap at a time. Chapter 4. The Cerebral Cortex. The outer surface of the human brain looks less like engineered technology and more like something hastily folded to fit inside itself. Wrinkled, compressed, uneven. Like a sheet of paper crumpled in someone's fist and only partially smoothed back out. Those folds are the cerebral cortex, a thin outer layer of neural tissue responsible for much of what humans associate with being consciously human. Language, reasoning, abstraction, imagination, planning, self-reflection, prediction. Everything feels impossibly fragile once you realize how thin it actually is. The cortex is only a few millimeters thick, a delicate layer of living cells folded repeatedly inside the skull because evolution ran into a geometry problem. Increasing intelligence required more surface area, But skull size could only expand so far before childbirth became impossible, so the brain folded inward instead. More folds meant more cortex. More cortex meant more neurons. More neurons meant more complex models of reality. Human consciousness may partly exist because biological tissue learned how to wrinkle efficiently, and yet the folds themselves are not organized cleanly. The cortex is not arranged like a perfectly designed machine. It resembles a dense living landscape shaped through millions of years of evolutionary compromise. Different regions specialize in different functions, but boundaries blur constantly. The frontal lobe helps construct plans, inhibit impulses, simulate futures, regulate behavior. The occipital lobe transforms patterns of light into visual reality. The temporal lobe processes sound, memory, language. The parietal lobe integrates sensory information and spatial awareness. But nowhere inside the cortex does anyone find a central observer. No theater where consciousness sits watching reality unfold. No singular location where the self definitively exists. Only distributed activity. Networks interacting with networks. Predictions updating predictions. That last part may be the most important. Increasingly, neuroscience suggests the cortex is not primarily reacting to reality. It is predicting it. The brain receives incomplete sensory data and continuously generates internal models to anticipate what comes next. Vision, hearing, movement, emotion. Even the perception of time may rely heavily on predictive processing. You are not passively seeing the world. Your brain is constructing expectations and correcting them in real time. In a sense, perception itself may be controlled, hallucination constrained by incoming sensory information, which explains why the cortex can be fooled so easily. Optical illusions work because the brain predicts incorrectly. Phantom limb pain occurs because the body map remains active after amputation. Dreams feel real because the cortex can generate internally coherent worlds without external input. Psychedelics may disrupt filtering and predictive stability, allowing raw sensory and associative processes to emerge more freely. Reality, as consciously experienced, is partly a simulation maintained by neural prediction, and most of that construction happens outside awareness. One of the strangest discoveries in neuroscience is how late consciousness seems to arrive in the process. Experiments repeatedly show measurable neural activity associated with decisions appearing before subjects consciously report making those decisions. Motor systems prepare actions before conscious awareness catches up. The brain initiates. Consciousness narrates, which raises a deeply uncomfortable possibility. The conscious self may not be directing thought as much as observing it. You do not decide to have most thoughts. They appear. You do not consciously regulate heartbeat, hormonal balance, emotional reflexes, sensory filtering, memory consolidation, or the vast majority of prediction occurring inside the cortex every second. The subconscious brain handles almost everything first. Then consciousness experiences the result and constructs a story of agency afterward. And yet, subjectively, the illusion of authorship feels complete. That tension sits at the center of modern neuroscience. The feeling of being a unified self may itself be a construction generated by distributed cortical systems. Split brain patients reveal this in unsettling ways. When the connection between hemispheres is surgically severed, the brain can begin behaving as if two semi-independent systems are operating simultaneously. One hand performs actions the other seems unaware of. One hemisphere generates explanations for behaviors initiated elsewhere. The mind improvises coherence even when coherence partially breaks down. The cortex appears deeply committed to maintaining the narrative of a singular self, even when evidence suggests fragmentation underneath. Damage reveals even more. A small lesion can erase language while leaving intelligence intact. A tumor can alter morality or impulse control. Degeneration can dissolve autobiographical memory until a person no longer recognizes their own life. Electrical stimulation of certain cortical regions can trigger memories, sensations, distortions of body ownership, or out-of-body experiences. The self is neurologically editable, and the more we discover, the stranger identity becomes. Because the cortex does not merely process the external world, it models itself. Humans possess recursive awareness, the ability to think about thinking, observe observation, reflect on consciousness itself. A brain made of matter somehow became capable of questioning its own existence. That recursion may be one of the strangest phenomena in nature. The cortex constructs models of reality, then constructs models of itself inside reality, then questions whether those models are accurate. Matter reflecting inward infinitely. And despite extraordinary advances in neuroscience, nobody fully understands how subjective experience emerges from cortical activity. We can observe neural correlates of consciousness, map functional networks, track synchronization patterns, measure electrical oscillations, decode aspects of perception from brain activity. But explanation keeps stopping one layer short. We can describe mechanisms, not why experience exists at all. Why should electrical activity feel like something from the inside? Why should specific patterns of neurons produce the redness of red, the sensation of cold air, the feeling of grief, or the awareness of being alive? The cortex remains deeply mysterious, precisely because it appears capable of generating an internal world while simultaneously hiding most of its own operations from conscious access. You experience the finished construction, not the process itself, which may explain why consciousness feels unified, even though the underlying system is massively distributed, recursive, predictive, and partially fragmented beneath awareness. And every night, even during sleep, the cortex continues working, reorganizing memories, updating predictions, simulating futures, generating dreams, strengthening pathways, weakening others. The folds never truly rest. A wrinkled sheet of living tissue suspended in darkness, endlessly attempting to predict reality, while also trying to understand itself. And perhaps that is the strangest part of all. The human cortex may be the first structure in the known universe capable of becoming aware of its own incompleteness. Chapter 5. At the base of the human brain, just above where the spinal cord disappears into the body, sits a structure that does not care about your ambitions, beliefs, identity, or plans for the future. It only cares that you continue breathing. The brainstem is ancient. Long before humans developed language, mathematics, philosophy, religion, or self-awareness, evolution had already built systems capable of regulating heartbeat, swallowing, breathing, blood pressure, and reflexive survival behaviors. The brainstem is part of that inheritance, one of the oldest and most conserved structures in the nervous system. Fish have versions of it. Reptiles have versions of it. Most mammals rely on nearly the same underlying architecture, which means the most fundamental systems keeping you alive are older than thought itself. From the outside, the brainstem looks surprisingly unimpressive, a narrow stalk of tissue. Compact, dense, almost fragile looking, and yet damage to a tiny region can instantly end consciousness, stop breathing, collapse autonomic regulation, or trap someone in a condition where awareness may remain while movement disappears entirely. The boundary between life and death runs through structures only centimeters wide. That fact becomes difficult to emotionally process once you understand what the brainstem is actually doing every second, right now, without your conscious involvement. Breathing rhythm is being regulated. Blood pressure is being monitored. Oxygen levels are being measured. Heart rate is adjusting continuously. Reflex systems are standing by. Muscles controlling. Swallowing and airway protection remain coordinated, and none of this requires conscious thought. You do not decide to breathe most of the time. You can temporarily interfere with the process. Hold your breath, hyperventilate, deliberately change rhythm, but eventually, the brainstem overrides conscious intention. Carbon dioxide levels rise. Emergency signals intensify, and survival systems reclaim control automatically. The deeper layers of the brain are patient but stubborn, which raises an unsettling possibility. The systems you consciously identify as yourself are not fully in charge of your body. Consciousness rides on top of older biological machinery. The cortex may generate stories, plans, beliefs, philosophies, and identities. But beneath all of it, the brainstem quietly maintains existence itself, a kind of biological metronome. And unlike the conscious mind, it does not sleep. Even during unconsciousness, anesthesia, coma, or dreaming, brainstem systems continue monitoring the body relentlessly. Throughout the night, while dreams distort reality and consciousness drifts through fragmented internal worlds, the brainstem keeps checking oxygen levels and maintaining respiratory rhythm. The ancient machinery continues working beneath the dream. Hospitals make this especially visible. Late at night, monitors beep steadily in dark rooms, while machines track respiration, pulse, blood oxygen saturation, and reflex responses. Every number represents survival systems operating moment by moment. If the rhythms destabilize, alarms sound immediately. Not because the hospital understands consciousness fully, not because anyone has solved the mystery of awareness, but because the body's deeper systems are measurable. The strange thing is how emotionally invisible the brainstem normally feels. You notice your thoughts. You notice emotions. You notice memories, desires, anxiety, imagination. But you rarely notice the systems preventing you from choking on your own saliva. The brainstem operates beneath narrative awareness, which may be why injuries involving it feel uniquely existential. Damage to higher cortical regions can alter personality, memory, language, impulse control, even identity itself. But severe brainstem damage threatens something even more fundamental: the ability for consciousness to remain connected to the body at all. And neuroscience still struggles to define exactly where that threshold exists. Some patients lose higher cognitive function, while basic autonomic activity continues. Some remain partially conscious, despite catastrophic injuries. Others enter locked-in states, fully aware internally, but almost completely unable to move or communicate externally, because pathways between consciousness and motor systems have been severed. A functioning mind trapped behind biological silence. Cases like these destabilize simplistic ideas about consciousness, because they reveal how fragmented the system actually is. Awareness, movement, emotion, memory, language, breathing, wakefulness. These are not generated by one unified center. They emerge from interacting systems layered across evolution. The brainstem handles survival. The limbic system shapes emotional salience. The cortex builds abstract models and conscious interpretation. Network interactions maintain wakefulness and integration. The self is distributed, and once you start examining the brain closely, the feeling of being a singular, unified I becomes harder to locate physically, especially because the brainstem itself appears almost indifferent to identity. It does not care about your political beliefs, your favorite memories, your fears about the future, your sense of meaning. It maintains heartbeat, whether you are having a spiritual revelation or an existential crisis. That indifference can feel strangely unsettling. The deeper biological systems sustaining consciousness are not philosophical. They are regulatory, mechanical in some ways, but also adaptive, ancient, and extraordinarily resilient. And yet even these ancient systems remain vulnerable. A clot, a lesion, swelling, loss of oxygen. Tiny physical disruptions can separate consciousness from the body within minutes, which forces another uncomfortable realization. Human awareness depends on continuous biological maintenance. The self is not floating independently above the nervous system. It is metabolically expensive, electrically active, chemically regulated, fragile. And still, despite all this, subjective experience persists. Somewhere above the brainstem's survival rhythms, higher networks generate dreams, language, imagination, memory, fear, and the persistent sensation of being someone moving through time. No one fully understands how these layers combine into conscious awareness. But the brainstem reveals something important very early. Before the brain became capable of understanding reality, it first had to survive it. And maybe that evolutionary layering still exists inside all of us. An ancient biological core maintaining respiration in darkness, while newer systems construct identity, narrative, philosophy, and the illusion of control above it. Even now, as you listen, the brainstem continues its work automatically, measuring, regulating, adjusting, repeating. An old evolutionary rhythm quietly counting time beneath consciousness itself, never asking permission, never needing applause, simply refusing, moment by moment, to let the lights go out. Chapter 6. The cerebellum sits quietly at the back of the brain, like a system nobody notices until it fails. Small, dense, folded tightly into itself. It looks almost secondary compared to the massive cerebral cortex above it. And yet more than half the neurons in your entire nervous system are packed into this structure alone. That fact surprises a lot of people. The part of the brain most associated with conscious identity, language, philosophy, imagination, and self-awareness contains fewer neurons than the strange wrinkled structure silently keeping you balanced while you walk across a room. The cerebellum rarely enters ordinary consciousness. You do not feel it adjusting your posture. You do not notice it correcting your hand while reaching for a glass. You do not consciously compute the tiny muscular changes required to stay upright while turning your head. And yet those calculations happen continuously. The cerebellum operates like a prediction and correction engine for movement. Every action your body attempts is compared against incoming sensory feedback in real time. Tiny errors are detected almost instantly and adjusted before conscious awareness notices anything happened. You reach for a mug. Your hand drifts slightly. The cerebellum corrects trajectory automatically. You walk across uneven ground. Your balance shifts. Micro adjustments stabilize posture before you consciously register instability. The corrections happen so quickly and seamlessly that movement feels effortless, which is fascinating because it means much of what humans experience as physical agency is actually unconscious automation. You do not consciously coordinate most movement. You experience the result after deeper systems already handled the complexity. That pattern keeps appearing throughout neuroscience. The subconscious brain performs the overwhelming majority of processing first. Consciousness arrives late, and the cerebellum may be one of the clearest examples of this principle because it reveals how much intelligence exists outside awareness. Learning a skill makes this especially obvious. The first time someone rides a bicycle, movements feel unstable and deliberate. Every correction requires attention. Balance feels fragile. The body overcompensates constantly. But with repetition, something changes. The movement becomes automatic. Neural pathways strengthen. Predictions improve. Corrections become more precise. Eventually, the conscious mind steps back almost entirely. You no longer think through every adjustment consciously because the cerebellum has internalized the patterns deeply enough to handle them automatically. This is procedural learning, the brain converting repeated behavior into subconscious prediction. The same thing happens with typing, playing instruments, sports, driving, speaking, dance, martial arts, even aspects of social interaction. Practice physically rewires the nervous system, until conscious oversight becomes less necessary. Which raises an interesting philosophical question. How much of human identity is simply reinforced automation? Habits become circuitry. Repeated emotional responses strengthen pathways. Behavioral patterns stabilize through repetition. The brain trains itself constantly, and much of what people call personality may partly emerge from deeply reinforced predictive systems operating beneath awareness. The cerebellum also reveals something important about prediction itself. Increasingly, neuroscience suggests the brain is fundamentally anticipatory rather than reactive. The nervous system continuously models future states and updates behavior before events fully unfold. The cerebellum predicts where your body will be milliseconds from now. The visual cortex predicts incoming sensory patterns. Emotional systems predict threat and reward. Higher cortical systems predict social outcomes, language, and behavior. The brain is constantly simulating the future. In many ways, consciousness may be less about directly experiencing reality and more about managing prediction errors between expectation and incoming information, which makes the cerebellum philosophically interesting, despite being associated mostly with movement, because it demonstrates how deeply prediction is embedded into biological intelligence, and it does all this silently. Most people never think about the cerebellum unless something goes wrong. Damage can be devastating. A person with cerebellar injury may struggle to walk smoothly, maintain balance, coordinate speech, or control precise movement timing. Tasks that normally feel automatic suddenly become conscious, awkward, exhausting. A hand reaches too far. A step becomes unstable. Speech rhythm changes. The body loses fluidity. The world begins requiring conscious correction, where subconscious systems once handled everything automatically. And there is something unsettling about that transition, because it exposes how artificial the feeling of effortless control really is. Grace is engineered invisibility. You only notice the machinery when the machinery fails. This theme appears everywhere in neuroscience. Vision feels immediate until visual processing disorders distort it. Memory feels stable until degeneration fragments it. Identity feels unified until split brain surgery challenges it. Agency feels conscious until experiments reveal subconscious decision activity appearing first. The brain hides its own complexity from itself. And perhaps that concealment is necessary. If conscious awareness had direct access to every correction, prediction, signal, and feedback loop occurring every second, ordinary functioning might become impossible. The nervous system filters most internal operations automatically, so consciousness can experience a simplified, coherent version of reality. You experience the finished performance, not the billions of hidden edits underneath it. The cerebellum embodies that hidden editing process perfectly. A silent system constantly refining movement before mistakes fully emerge into awareness. Correcting, predicting, stabilizing, rehearsing. And perhaps that extends beyond physical coordination. Some researchers increasingly suspect the cerebellum may contribute to cognition, emotion, timing, prediction, and even aspects of thought itself. The same predictive architecture used to refine movement may also help refine mental processes. which would fit a larger pattern inside the brain. The same fundamental mechanisms repeating across different layers of consciousness. Prediction, correction, reinforcement, adaptation. The brain learning itself through feedback. And like so many structures in neuroscience, the cerebellum raises a deeper existential question once you examine it long enough. If enormous portions of intelligence, coordination, prediction, and behavior occur outside awareness, then what exactly is consciousness contributing? The conscious self feels central, authoritative, in control. But underneath that feeling, hidden systems are constantly managing reality before awareness catches up. The cerebellum does not ask permission before stabilizing your body. It does not explain its calculations. It does not narrate what it corrected. It simply acts. Quietly. Continuously. Automatically. A folded mass of neurons suspended in darkness. Refining your interaction with reality thousands of times per second, while remaining almost completely invisible to conscious experience. And perhaps that invisibility is the point. The most important systems in the brain are often the ones you never notice at all. Chapter 7. The Limbic System. Buried deep beneath the cerebral cortex, below the systems responsible for language, logic, and deliberate reasoning, sits an older network that cares far less about truth than survival. The limbic system does not ask, "Is this rational?" It asks, "Does this matter?" And that distinction shapes nearly every human experience. A certain smell suddenly pulls you backward through time. A song reactivates emotions you thought had disappeared years ago. A face feels trustworthy before you can explain why. A sound in the dark triggers fear before conscious thought catches up. The emotional brain reacts first. Then consciousness builds explanations afterward. That pattern appears constantly throughout neuroscience. The subconscious system initiates. The conscious self narrates. The limbic system is not a single structure, but a collection of interconnected regions deeply involved in emotion, memory, motivation, reward, and survival relevance. At its center are structures like the hippocampus, involved in forming new memories. The amygdala, heavily associated with emotional salience and fear processing. Interconnected reward and motivational circuits shaped by dopamine and reinforcement. Together, these systems determine what the brain treats as important enough to remember. Because memory is not objective recording. The brain does not archive experience like a camera storing footage. Memories are reconstructed dynamically, filtered through emotion, attention, stress, expectation, and biological state. What you remember is partly determined by what the limbic system decided mattered emotionally at the time. That's why emotionally intense experiences feel unusually vivid. Fear strengthens encoding. Novelty strengthens encoding. Shame strengthens encoding. Love strengthens encoding. Trauma strengthens encoding. Emotion acts like a biological highlighter across memory formation, and sometimes the emotional imprint survives even when the factual details fade. A person may forget names, dates, conversations, or chronology, while still retaining the emotional atmosphere of an event decades later. The body remembers what the narrative mind cannot fully reconstruct, which makes memory feel strangely alive compared to storage systems in machines. Human memory changes every time it is recalled. Each retrieval slightly rewrites the memory itself, meaning the past inside your brain is not fixed. It evolves. The self is partially reconstructed each time you remember being yourself. And nowhere does this become more unsettling than in cases involving damage to the limbic system. Injury to the hippocampus can prevent new long-term memories from forming entirely. A person may remain intelligent, conversational, emotionally expressive, yet unable to reliably store new experiences. Consciousness continues unfolding moment by moment, while continuity collapses. The present becomes disconnected from the future. Damage to the amygdala produces something equally strange. Certain patients with bilateral amygdala damage lose much of their normal fear response. Threat detection weakens dramatically. Dangerous situations fail to generate appropriate emotional salience, which raises a difficult question. If fear can be surgically altered, how much of personality is biological architecture rather than conscious choice? Fear feels deeply personal from the inside. Moral, psychological, meaningful. But neuroscience increasingly reveals how dependent emotion is on specific circuitry. A tiny lesion can alter emotional behavior profoundly. The boundary between who you are and neural configuration becomes disturbingly thin. And yet, the limbic system is not merely primitive emotional machinery. It is predictive. Like the rest of the brain, it continuously anticipates significance. The amygdala often reacts before conscious recognition fully forms. Sensory information can trigger rapid emotional responses milliseconds before higher cortical interpretation catches up. You jump first, then understand why afterward. Experiments repeatedly demonstrate this lag between subconscious processing and conscious explanation. The emotional brain evaluates threats, social cues, and relevance rapidly, while consciousness receives a partially processed version later, which may explain why human beings are so skilled at rationalization. The conscious mind often behaves less like a commander and more like a press secretary, explaining decisions already made elsewhere. That possibility unsettles people because it destabilizes intuitive ideas about agency. We experience ourselves as consciously directing behavior, but much of what drives human life emerges from subconscious systems shaped by reinforcement, emotion, memory, hormones, prediction, and survival pressures. The limbic system sits near the center of that machinery. It determines what feels meaningful. And meaning itself may be more biological than people prefer to admit. Nostalgia is chemistry. Attachment is circuitry. Reward is neurotransmission. Trauma physically reshapes neural pathways. Repeated emotional states strengthen future emotional tendencies. Experience becomes architecture. The emotional brain trains itself constantly, and once patterns form deeply enough, they begin influencing perception automatically. An anxious brain predicts threat more easily. A traumatized brain scans for danger continuously. A lonely brain becomes hypersensitive to rejection. An addicted brain prioritizes reward pathways over long-term stability. Emotion changes prediction. Prediction changes perception. Perception reinforces emotional expectation. The brain becomes a feedback loop, training itself through lived experience, which may explain why feelings can feel inescapable even when intellectually understood. You cannot simply reason yourself out of many emotional responses because the systems generating them evolved earlier and operate faster than conscious reflection. The cortex can reinterpret emotion, sometimes regulate it, sometimes suppress it temporarily. But the deeper emotional machinery often moves first. And perhaps that is why certain memories feel almost physical. A photograph, a smell, a hallway, the sound of ice in a glass, a specific season, a familiar voice. Suddenly, the nervous system reconstructs an entire emotional state from fragments. Not because memory is perfectly accurate, but because emotional associations remain deeply embedded across interconnected networks. The limbic system stores significance more than facts, and significance shapes reality. Modern neuroscience increasingly suggests humans do not merely perceive the world objectively. Emotional systems help determine what enters conscious awareness in the first place. The brain filters reality based partly on predicted importance. You notice what the nervous system believes matters for survival, attachment, reward, identity, or threat. The rest fades into background noise, which means no two people inhabit precisely the same reality internally. Every brain constructs experience through slightly different emotional architecture, shaped by genetics, memory, trauma, reinforcement, culture, and personal history. Reality becomes personalized prediction. And despite all this biological complexity, subjective emotion still feels mysterious from the inside. No scan fully captures grief. No equation explains nostalgia. No neural map fully accounts for why certain memories ache while others comfort. Science can identify correlations, mechanisms, networks, chemical influences, but explanation still stops short of experience itself. The feeling remains. Somewhere inside layered emotional circuitry, electrical activity becomes longing, attachment, embarrassment, fear, love, memory, and the persistent sensation that certain moments mattered. The limbic system does not preserve the world objectively. It preserves what hurt, what comforted, what frightened, what bonded, what survived. A biological archive shaped less by truth than by emotional consequence. And even now, beneath conscious awareness, those systems continue sorting experience silently, tagging moments, strengthening associations, reinforcing patterns, preparing future emotional predictions. An ancient emotional intelligence suspended beneath the thinking mind, quietly deciding what will stay with you long after the details disappear. Chapter 8. Plastic Brain. The human brain is not fixed. It is not finished at adulthood. It is not static after childhood. It does not simply store information like files placed into drawers. The brain changes itself continuously. Every experience leaves physical traces. Every repeated thought reinforces pathways. Every fear reaction strengthens associations. Every habit deepens circuitry. Every memory slightly rewrites the system remembering it. You are not using the same brain you had 10 years ago. In a very literal, biological sense, experience has been reshaping it the entire time. This process is called neuroplasticity, the brain's ability to reorganize itself structurally and functionally through repetition, learning, injury, emotion, and adaptation. And once you understand it, the self begins to feel less permanent than it appears from the inside. The old idea in neuroscience was that the adult brain became relatively fixed after development. Childhood shaped the architecture. Adulthood merely operated within it. That assumption turned out to be deeply wrong. The nervous system remains adaptable throughout life, not infinitely, not effortlessly, but continuously. Neurons strengthen frequently used connections. Unused pathways weaken. Networks reorganize in response to behavior, injury, stress, repetition, environment, and attention. The brain is always training itself, which means every repeated experience is also rehearsal. Practice a movement enough times and it becomes automatic. Repeat an emotional response long enough and it becomes easier to trigger. Rehearse anxiety daily and the nervous system becomes more efficient at producing anxiety. Practice calmness repeatedly and different pathways strengthen instead. The brain learns patterns regardless of whether those patterns are healthy. That is one of the more unsettling aspects of neuroplasticity. The nervous system does not inherently distinguish between useful adaptation and destructive adaptation. Addiction is neuroplasticity. Trauma is neuroplasticity. Chronic fear is neuroplasticity. Compulsive behavior is neuroplasticity. The brain becomes what it repeatedly does. And because repetition physically alters synaptic strength, habits begin feeling automatic over time. At first, conscious effort dominates behavior. Then pathways strengthen. Predictions stabilize. Actions require less awareness. Eventually, the subconscious system takes over. Again and again, neuroscience arrives at the same disturbing pattern. Consciousness may contribute far less direct control than people intuitively believe. The deeper systems learn first. Then consciousness experiences the results afterward. And yet neuroplasticity is also one of the most hopeful discoveries in modern neuroscience, because it means the nervous system can recover. Stroke patients sometimes relearn movement after entire regions become damaged. People recover language through retraining alternative pathways. Blind individuals recruit visual cortex regions for touch and spatial processing. Musicians physically reshape motor and auditory networks through years of practice. The brain improvises around injury, not perfectly, not cleanly, but persistently. A damaged nervous system often attempts to reroute itself through remaining pathways, creating new strategies for accomplishing old functions. There are even extraordinary cases where children lose entire hemispheres of the brain due to severe epilepsy, and still recover remarkable levels of function over time. Language migrates. Motor systems adapt. Networks redistribute responsibility. The system is astonishingly flexible, and at the same time, deeply constrained. Because neuroplasticity is not magic. Old patterns rarely disappear completely. The brain does not erase itself cleanly. It layers. An addiction pathway weakened through years of recovery may still reactivate under the right triggers. A traumatic memory can resurface decades later with startling intensity. An old emotional pattern can re-emerge under stress almost instantly. The nervous system remembers previous configurations even while building new ones, which makes personal change feel psychologically strange. People often imagine transformation as replacement, becoming an entirely different person. But biologically, change is usually additive. New pathways strengthen over older ones. Alternative responses become more accessible. Different predictions become more likely. The old circuitry often remains buried underneath, which may explain why certain memories, habits, fears, or emotional states can suddenly reappear after years of seeming dormant. The previous version of the self was never fully deleted, only overwritten. And perhaps that is why neuroplasticity feels philosophically important in a way that extends beyond neuroscience, because it destabilizes the idea of identity as fixed. If repeated experience physically reshapes perception, emotion, prediction, and behavior, then the self is not a stable object. It is an ongoing process, a continuously edited biological pattern. Even memory itself participates in this instability. Every time you remember something, the brain reconstructs it rather than retrieving a perfectly preserved recording. The memory becomes temporarily malleable during recall, then stored again in slightly altered form. The act of remembering changes the memory, which means your internal past evolves over time. The self is partly rewritten through recollection itself, and none of this occurs in isolation. The brain is constantly adapting to stress, sleep, social interaction, trauma, technology, repetition, attention, environment, emotional reinforcement, expectation. Experience becomes structure. Modern neuroscience increasingly suggests that much of human reality emerges from learned prediction loops reinforced over time. The brain anticipates based on prior experience, and those predictions shape future perception. You see partly what your nervous system expects to see. You fear partly what your brain has learned to fear. You notice what your networks predict matters. Reality becomes filtered through accumulated adaptation, which may explain why changing deeply rooted behaviors can feel so difficult. You are not merely changing ideas. You are attempting to reshape living circuitry built through repetition across years or decades. The brain resists sudden reorganization because predictive stability is biologically efficient. Familiar patterns consume less energy and produce fewer surprises. The nervous system prefers certainty over accuracy surprisingly often, and yet adaptation never fully stops. Even aging brains continue changing. New synapses form. Existing pathways strengthen or weaken. Learning remains possible. Recovery remains possible. Reinvention remains possible. The final draft never arrives. And perhaps that is the deeper emotional significance of neuroplasticity. The self is not something permanently discovered. It is something continuously constructed, moment by moment, The brain rewires itself through experience while simultaneously generating the feeling of being a stable person moving through time. A system constantly editing itself while trying to preserve the illusion of continuity. And somewhere inside that process, consciousness keeps narrating the story as though it had always been this version of itself. Even now, as you listen, microscopic changes are occurring inside your nervous system. Synapses strengthening, associations forming, predictions updating, pathways reinforcing themselves quietly beneath awareness. The brain reshaping itself around experience in real time. A living system, writing and rewriting its own architecture endlessly in darkness. Chapter 9. The human brain contains roughly 86 billion neurons. That number is difficult to visualize, so people often reduce it to metaphors. Cities, galaxies, forests, wiring diagrams. But none of those comparisons fully capture what the brain actually is, because neurons alone are not enough. What matters is the pattern of connections between them, the pathways, the roots, the feedback loops, the tangled architecture continuously shaping thought, memory, identity, and behavior. This vast network is called the connectome, the total map of neural connections inside the brain, and in many ways, it may be closer to you than the individual neurons themselves. A single neuron means almost nothing in isolation. Consciousness emerges from relationships, from signals moving through networks, from patterns reinforcing other patterns, from loops stabilizing over time until a coherent self appears to exist. The connectome is less like a machine blueprint and more like a living ecosystem, constantly rewriting itself. Every experience slightly alters it. A conversation changes it. A trauma changes it. Learning a language changes it. Falling in love changes it. Addiction changes it. Grief changes it. Sleep changes it. Dreams may change it. The brain is continuously editing its own structure while simultaneously generating the feeling of personal continuity, which is strange when you stop and think about it, because the self feels stable from the inside. You wake up each morning believing you are fundamentally the same person you were yesterday. But biologically, the network underneath that feeling has already shifted. Connections strengthened. Others weakened. Predictions updated. Associations reinforced. Memories reconstructed slightly differently. The connectome is dynamic, and no two are identical. Even identical twins raised together develop different neural architectures over time because experience physically sculpts connectivity. Childhood environments, emotional states, social interactions, stress, repetition, injury, habits, fears, relationships, language, culture, all of it leaves traces inside the wiring. Every human mind becomes a unique pattern of accumulated adaptation, which may explain why subjective reality differs so dramatically from person to person. No two nervous systems predict the world in exactly the same way. The brain does not merely receive reality objectively. It filters, compresses, prioritizes, predicts, and reconstructs it using existing networks shaped through prior experience. Your connectome partly determines what you notice, what you fear, what you remember, what feels meaningful, what feels familiar, what patterns your brain expects to encounter. In a very real sense, the brain builds a personalized model of reality using its own accumulated wiring history. And perhaps nowhere does this become more unsettling than in split-brain patients. The corpus callosum, a massive bundle of neural fibers connecting the left and right hemispheres, normally allows information to flow between both sides of the brain. In severe epilepsy cases, surgeons sometimes severed this connection to reduce seizure spread. What followed challenged the idea of a singular unified self. Patients occasionally displayed signs suggesting semi-independent processing between hemispheres. One hand performs an action the other seems unaware of. One hemisphere reacts emotionally, while the verbal system invents explanations afterward. Conflicting intentions appear simultaneously within the same body. And perhaps most unsettling of all, the brain often hides these contradictions from conscious awareness by generating coherent narratives after the fact. The mind improvises continuity. That pattern appears repeatedly throughout neuroscience. Consciousness seems less like a centralized commander and more like a constructed interface emerging from distributed systems interacting beneath awareness. The connectome reinforces this idea because there is no single location where the self resides, no central control room, no hidden observer, no solitary neuron containing identity, only networks. Vast layered systems exchanging signals continuously through pathways shaped by prediction, memory, reinforcement, emotion, and survival. The self may be a process rather than an object, a stable pattern emerging from unstable activity. And modern neuroscience has only mapped fragments of it. Researchers use imaging techniques like diffusion tensor imaging to trace major neural highways by tracking how water molecules move along axon bundles. Large-scale pathways become visible, connections between hemispheres, motor networks, sensory integration systems. But these are only rough sketches. The true connectome operates at scales almost impossible to fully capture. Trillions of synapses, microscopic branching structures, constant rewiring, dynamic feedback loops changing moment to moment. Even mapping the entire nervous system of tiny organisms required enormous effort. The fully mapped connectome of the worm C. elegans, one of the first complete connectomes ever constructed, contains only 302 neurons. The human brain contains billions. The complexity difference is almost incomprehensible, and yet despite this impossibility, the connectome may hold clues to some of the deepest questions in neuroscience. How memories stabilize, how identity persists, how emotional associations form, how prediction shapes perception, how consciousness emerges from distributed activity, or perhaps it may reveal something even stranger, that the self was never singular to begin with. Because the deeper scientists look, the harder it becomes to locate a unified I inside the system. There are emotional systems, motor systems, prediction systems, attention systems, language systems, reward systems, threat detection systems, but no obvious central observer tying everything together. Only coordination. And coordination can fracture. A lesion changes personality. A seizure disrupts continuity. A psychedelic alters perception. Sleep paralysis traps awareness between systems. Dreams generate internally coherent realities, disconnected from external input. The connectome is stable enough to produce continuity, flexible enough to change constantly, fragile enough to break, and still, subjectively, consciousness feels singular. That may be one of the brain's most remarkable achievements. Constructing the persistent illusion of a unified self from massively distributed biological activity. Or perhaps illusion is the wrong word. Maybe the self is real in the same way a whirlpool is real, not a fixed object, but a stable pattern emerging from continuous motion. The connectome may function similarly, a living network maintaining temporary coherence while every component changes over time. And even now, as you listen, your own connectome continues reorganizing itself. Signals strengthening pathways, memories modifying associations, predictions adjusting future perception, experience reshaping structure, silently beneath awareness. A vast biological web continuously weaving the next version of you in darkness. Never fully finished. Never fully stable. Always becoming something slightly different than it was a moment before. Chapter 10. Machines and Minds. For a long time, humans have compared the brain to the most advanced machine available at the time. Clockwork, hydraulic systems, telephone switchboards, computers. Each metaphor feels convincing briefly. Then neuroscience pushes past it. The computer comparison is the most persistent because on the surface it seems obvious. Both systems process information, store memory, transmit signals, respond to input, generate output. But the deeper you examine the brain, the more the comparison begins collapsing. Computers are precise. Brains are improvisational. A computer follows explicit instructions. The brain predicts, guesses, edits, fills gaps, and reconstructs reality continuously. A machine freezes when systems fail. The brain hallucinates coherence instead. That difference matters more than it first appears. A computer stores information discreetly. Exact files, exact locations, exact retrieval. Human memory does not work like that. The brain reconstructs memories dynamically every time they are recalled. Details shift. Emotions alter perception. Missing information gets unconsciously filled in. Entire events can be partially fabricated without the person realizing it. The brain values coherence over accuracy, surprisingly often. And perhaps nowhere is this more unsettling than in split brain experiments. When the corpus callosum connecting the hemispheres is severed, the brain can begin generating contradictory behavior between sides of the body. One hemisphere initiates actions the verbal system cannot fully explain, but instead of admitting uncertainty, the conscious mind often invents explanations automatically. A person performs an action. Consciousness generates a story afterward. The story feels true. This phenomenon, confabulation, reveals something deeply strange about human awareness. The mind would often rather create meaning than tolerate ambiguity. The conscious self may function less like a central controller and more like a narrative engine maintaining continuity after subconscious systems already acted. Again and again, neuroscience keeps pointing toward the same unsettling possibility. The feeling of being a unified conscious author may itself be a constructed experience. Computers do not do this. A machine encountering missing information produces an error. The human brain produces interpretation, and interpretation is messy. The nervous system constantly predicts incoming reality rather than passively recording it. Sensory information arrives incomplete, delayed, noisy, and fragmented. The brain fills the gaps automatically using prior experience and predictive modeling. You do not consciously experience raw sensory data. You experience the brain's best real-time simulation of reality. Some neuroscientists describe perception itself as controlled hallucination. That phrase sounds extreme until you realize how much editing occurs beneath awareness. Your blind spot is filled automatically. Visual continuity is constructed. Auditory gaps are repaired subconsciously. Time itself may be partially assembled through predictive integration. The world feels stable because the brain is extraordinarily good at hiding its own processing. Computers render images pixel by pixel. Brains generate meaning from approximation. And unlike machines, the brain is never fully still. Even at rest, neural networks remain active, dreaming, predicting, replaying memories, reorganizing pathways, simulating futures, maintaining internal models. The default state of the brain is not silence. It is wandering. A computer waits for input. The brain generates its own. Thoughts emerge spontaneously. Memories surface without request. Songs replay involuntarily. Dreams construct worlds autonomously during sleep. The nervous system continuously produces internal activity, whether conscious awareness wants it or not, which raises an uncomfortable question. If thoughts simply appear inside consciousness, then who exactly is choosing them? Most people experience themselves as consciously generating thought. But introspection reveals something stranger. You do not decide your next thought before thinking it. It arrives. Consciousness observes. The deeper systems generate. Modern neuroscience increasingly suggests that subconscious processes initiate enormous amounts of cognition before awareness catches up. Motor preparation, emotional evaluation, predictive modeling, and associative processing occur automatically beneath conscious access. The conscious self experiences the output. This does not necessarily eliminate free will entirely, but it radically complicates simplistic notions of conscious authorship. And unlike computers, the brain evolved for survival rather than truth. That distinction explains many cognitive distortions. The nervous system compresses reality aggressively, filters irrelevant information, builds emotional biases, creates shortcuts, prioritizes prediction efficiency over objective accuracy. Human perception is adaptive, not neutral, which is why hallucinations, dreams, and altered states become philosophically important rather than merely pathological. Dreams reveal the brain's ability to generate convincing realities internally while disconnected from external input. Psychedelics destabilize predictive filtering and sensory integration. Out-of-body experiences demonstrate how body ownership can be neurologically manipulated. Temporal lobe stimulation can trigger intense spiritual experiences or feelings of cosmic significance. The machinery generating reality can be altered chemically or electrically, and once you realize that, ordinary waking consciousness starts looking less solid than it first appeared. Computers also do not possess emotional salience systems in the way biological organisms do. A machine processes information without caring, but the human brain constantly assigns emotional weight: threat, reward, attachment, fear, meaning, nostalgia, beauty. The limbic system determines what matters long before conscious reasoning fully engages. Emotion shapes perception itself. A frightened brain literally experiences the world differently than a calm one. And perhaps that emotional instability is part of what makes consciousness feel alive rather than computational. Because the brain is not merely calculating, it is surviving, predicting, remembering, imagining, constructing identity, generating subjective experience, all simultaneously. And unlike machines, brains physically rewrite themselves through use. Every repeated behavior strengthens pathways. Every trauma reshapes emotional prediction systems. Every habit modifies connectivity. Every memory changes during recall. The system is dynamic. A computer executes code. The brain rewrites itself while running. That may be one of the deepest differences between artificial systems and biological minds. The brain is not simply processing information. It is continuously reconstructing the structure doing the processing. And despite all advances in neuroscience, the central mystery remains untouched. Why should any of this feel like something from the inside? A computer can process language without experiencing meaning. A chess engine can defeat grandmasters without feeling tension. An algorithm can generate responses without sensing existence. But somewhere inside biological tissue, electrical activity became subjective awareness. A system made of cells began asking questions about itself. And perhaps that is why the machine metaphor always eventually fails. Because no matter how advanced computers become, they still do not appear haunted by their own existence. The human brain does. Late at night, staring at a softly glowing monitor in a dark room, the distinction becomes difficult to ignore. The computer waits. The brain wanders. One executes. The other dreams. One processes signals. The other turns signals into reality itself. And somewhere inside those electrical storms, consciousness continues asking the strangest question imaginable. Why does any of this feel like being someone at all? Chapter 11. Sleep and Repair. Sleep is one of the strangest things the human brain does. Every night, consciousness disappears voluntarily. You lose awareness of the external world. Your muscles partially shut down. Your sense of time fragments. Reality dissolves into internally generated simulations. And while this happens, the brain becomes intensely active. Not inactive, not powered down, busy. For most of human history, sleep looked passive from the outside. A body lying still in darkness appears almost absent. But modern neuroscience revealed something far stranger. The sleeping brain continues processing, reorganizing, predicting, consolidating, repairing, and constructing experience throughout the night. In some phases, neural activity becomes nearly as intense as waking consciousness, which raises an unsettling question. If conscious awareness disappears for hours every night while the brain keeps working, then what exactly is the relationship between consciousness and the deeper system underneath it? Because sleep exposes something people rarely notice while awake. The conscious self is not supervising most brain activity. The nervous system continues operating without you. Breathing continues. Memory reorganizes. Emotional processing continues. Sensory systems partially monitor the environment. Dreams emerge automatically. Neural pathways strengthen or weaken. Waste products are cleared from tissue. The brain maintains itself, while consciousness temporarily lets go. One of the most fascinating discoveries in sleep research involves the brain's cleaning systems. During deep sleep, cerebrospinal fluid moves through brain tissue more aggressively, helping clear metabolic waste products accumulated during waking activity. Neural support cells shrink slightly, opening spaces that allow fluid exchange to increase. The brain literally washes itself during sleep, which means consciousness is metabolically expensive. Thinking generates waste. Perception generates waste. Attention generates waste. The act of being awake slowly accumulates biological residue requiring maintenance. Sleep is not optional downtime. It is neurological survival. And the effects of losing it become obvious quickly. Memory destabilizes. Emotional regulation deteriorates. Attention fragments. Reaction time slows. Prediction accuracy worsens. Hallucinations eventually emerge. The brain begins losing coherence. Because sleep deprivation does something deeply revealing. It destabilizes the brain's ability to maintain a consistent model of reality. The nervous system starts mispredicting. And perhaps that connection between sleep and prediction is important. Increasingly, neuroscience suggests the brain functions fundamentally as a predictive engine continuously generating internal models of reality. During waking consciousness, sensory input constrains those models. But during dreaming, external input largely disconnects. The brain begins simulating freely. Dreams are among the strangest products of human consciousness, because they reveal how easily the brain can construct entire realities internally. While asleep, the nervous system generates people, places, narratives, conversations, fear, desire, physics, time, identity. And during the dream, it usually feels real. That fact alone is philosophically disturbing. Because if the brain can generate convincing worlds internally while disconnected from external reality, then waking consciousness may also involve far more construction than direct perception. Some neuroscientists describe perception itself as controlled hallucination, constrained by sensory input. Dreams may simply remove most external constraints. The simulation continues running, and the emotional intensity of dreams reveals something else important. The brain does not require external reality to generate genuine subjective experience. Fear inside a nightmare feels real. Grief inside a dream feels real. Love inside a dream feels real. The nervous system responds emotionally to internally generated worlds almost as powerfully as external ones, which may explain why dreams sometimes linger psychologically long after waking. And yet, no one fully understands why dreams exist. There are theories: emotional processing, memory consolidation, predictive simulation, threat rehearsal, neural maintenance, associative integration. But no single explanation fully accounts for the bizarre creativity and emotional complexity of dreaming consciousness, especially because dreams often combine memories, fears, sensory fragments, symbolic distortions, impossible physics, people from different eras of life, and entirely invented scenarios. The sleeping brain behaves less like a logical machine and more like a reality generator, unconstrained by external consistency. And perhaps the strangest part is that consciousness usually accepts the dream without question while inside it. You rarely stop and say, "This makes no sense." The brain treats internally generated reality as reality until awakening interrupts the simulation. That realization destabilizes waking certainty in subtle ways. Because if consciousness can be fully convinced by dream worlds nightly, how much of waking experience depends on similarly constructed assumptions held together by stable sensory input? Sleep also reveals how incomplete conscious control really is. You cannot consciously force yourself into sleep directly. You cannot fully control dream content. You cannot consciously supervise memory consolidation while unconscious. You cannot stop the brain from continuing activity while awareness disappears. The deeper systems operate autonomously. Again and again, neuroscience points toward the same uncomfortable pattern. Consciousness may be less like a ruler and more like a temporary witness emerging from deeper biological processes. And sleep exposes that hierarchy clearly. The conscious self disappears temporarily. The underlying system continues. Perhaps that is why certain altered states surrounding sleep feel so existentially strange. Sleep paralysis traps awareness, while motor systems remain suppressed. Lucid dreaming introduces partial self-awareness into dream simulations. Hypnagogic states blur the boundary between imagination and perception. False awakenings create dreams about waking up. The borders between consciousness states become unstable. Reality feels less fixed than people assume. Even memory becomes unreliable around sleep. Most dreams vanish rapidly after waking because the brain prioritizes some information while discarding other parts automatically. Entire emotional worlds dissolve within minutes, which suggests forgetting itself is not a flaw. It is part of how the brain maintains functional coherence. A mind that retained every detail equally might become unusable. The nervous system edits constantly, strengthening, pruning, compressing, discarding. Sleep appears central to that process. And perhaps that is why people sometimes wake with solutions to problems they could not consciously solve the night before. While consciousness steps away, subconscious systems continue processing patterns in the background. Associations reorganize silently until insight surfaces later into awareness. The brain keeps thinking without the thinker. That idea feels almost paradoxical. The system generating consciousness continues operating independently of conscious supervision. And maybe sleep is unsettling for a deeper reason beyond vulnerability or unconsciousness. Every night, continuity breaks. The conscious self disappears temporarily. Experience fragments. Dreams distort identity. Memory partially resets. Then morning arrives, and the brain reconstructs the feeling of being the same person again. Most people never question this transition because it happens daily. But philosophically, it is strange. The self vanishes into unconsciousness for hours. A new stream of awareness resumes later, and the brain seamlessly presents continuity as though nothing interrupted it. Perhaps continuity itself is partly constructed retroactively, a stable narrative emerging from systems designed to preserve identity across interruptions. And even now, while you remain awake listening, deeper systems inside the brain are already preparing for the next descent into unconsciousness. Memory networks reorganizing, circadian rhythms shifting, predictions adjusting, dream architecture preparing itself silently beneath awareness. The nervous system waiting for consciousness to let go, so the deeper work can begin again. A biological universe hidden behind the eyes, continuing its activity through darkness, whether the conscious self is present to witness it or not. Chapter 12. The deeper neuroscience goes, the stranger the human brain becomes. At first, the brain seemed understandable in the way machines are understandable. Scientists identified neurons, electrical signals, brain regions, neurotransmitters. Each discovery felt like progress toward a final explanation. Map enough circuitry, and eventually consciousness should reveal itself. But something unexpected happened. The more mechanisms researchers uncovered, the harder the central mystery became. Because understanding components is not the same thing as